Okay, now we're good. Okay. So be honest, guys, who gave it a try, like on their own?
Like for 4 questions and then
For 4 questions, and then we were just like,
Yeah.
let's copy it. Okay. Okay, thank you. That's good. So please give it a try on your own, like without notes. Max take 2 hours to solve it because that's going to be a pretty good practice final for you guys. But let's go through some of the questions in here. Or do you guys have any specific problems that you wanted to go over?
go do it.
Okay, let's just go one by one. Okay. Okay, so the first one. Which of these compounds could not be formed by an nucleophilic attack by an appropriate reagent on acetyl chloride? First of all, that question, does it seem from which chapter? 17. Why did you say 17, Emily? The acetyl chloride is a leaving group, exactly. Whenever you see carbonyls with leaving groups, you should automatically think on chapter 17. Now, in this case, they were asking which one could not be formed with your acetyl, wait, can I, yeah. With your acetyl chloride. Oh, sorry. Okay, this guy. Acetyl chloride, how does that look like? Carbonyl with? And that's it. Okay, now, how would you try to solve this? I mean, yeah, chlorine is going to be your leaving group. I mean, of course, you guys right now have the answer, but how would you try to approach it? Yeah.
For this question, I just said what. So we've gone over how to make an amide. We've gone over how to make an ester.
Mm-hmm.
That Cl, that primary Cl on that carbon, that's awkward. Like I don't know how we would attach that in a reaction like that. We would.
It is awkward.
Mm-hmm. And then that's another. That's a carboxylic acid. We went over how to make those, and then the other one was anhydride.
Mm-hmm. Your acetic anhydride.
Acetic anhydride.
So
The only thing I was like, okay, that Cl on the left looks awkward. I don't know how to make that. That's my answer.
Exactly. So pretty much you can play around with the answer choices. So if you start freaking out because you don't remember certain concepts, play around with the answer choices. But let's clear all drawings and let's move. Okay. What chapter is this from?
Acid, that's like 11, 12. Is that the 16?
16, 17, 12. Okay, you have a carbonyl group with a leaving group. So it's chapter 17. Okay. Now, chapter 17, remember, it was all about basically just changing the leaving group. So you chop off that leaving group that you have, and then whatever you have on the arrow, in this case, it was presented separate, you're going to attach this guy instead. And he gave you an isotope to test you where exactly to add it, which the only one that shows it correctly is option A. If you put the oxygen 18 at the very top, like a carbonyl, that wasn't correct at all. Yeah. Yes, it's always one less hydrogen, so we don't create any charges in the end. One.
What's the mechanism? So the carbonyl gets protonated by the acid, right?
Mm-hmm.
So then it has that positive.
We have a positive in there.
And then the lone pair from the oxygen 18 comes under the carbonyl, right?
Mm-hmm. And then we kick up electrons.
So then that becomes
Whoops. Okay. This one would be O minus now, and we added the whole thing. So OH 18 with a methyl group, positive charge, and then OH.
Hold up, what was the carbonyl on this one?
The carbonyl was supposed to be over here.
So it comes in with a partial positive.
After we do the attack, remember, that's a nucleophilic attack, so we connect the reagent and the carbon that had a delta positive. Now, after that, because we have a leaving group, we can make it better by transferring a proton. So water would be the leaving group, which is
Okay.
way more stable. And then eventually reform double bond, kick out your leaving group. Do you remember the mechanism for this one?
So the shortcut would be take the carboxylic out, put in your.
Yes. Chop off leaving group, put whatever's on the arrow. Okay, we're good. No more questions on this one. We're good. God. Okay. Okay, and he twist them. Okay, this one. What chapter is it from?
17.
It is 17.
The
Yes.
17 was everything to do with the means, right? Means and amount.
We had a few chapters that had to do with amine. Is this a lactone? What was a lactone and a lactame? So lactones, remember, they're cyclic esters. Lactames, cyclic amides. In this case, whoops. This guy, what is it? What functional group is it?
It's like an anhydride.
It's an acidic anhydride, so we don't have a special name for that. If it was an ester, then yeah, it would be a lactone. Okay,
Wait, you said it was a what? So cyclic anhydride?
it's an acidic anhydride.
Acetic anhydride. Okay.
That's just the name of the common functional group. What do you say?
Oh, you're talking rate expansion? Right?
We open it, so just by knowing that leaving groups, we chop them off. So we can start discarding some answer choices. They don't make sense. Now, we know that at the end, I'm gonna be adding whatever's on the arrow, but I have to get rid of one of those extra hydrogens, so everything is neutral. So I know that if I add the nitrogen next to the carbonyl, I'm creating an amide. So I only have two answer choices that have amides. So we start discarding number one. Now, which one is going to be the answer, but and why? Because remember that your leaving group, it's still hanging from that molecule. You're not replacing that one. Okay, questions on that one?
Oh, okay. And I guess what threw me off, I guess was that.
That one just basically protonated your leaving group, so we can end up with an OH. Okay, this one. What chapter is that from?
This 16, right?
16 or 17? Why 16?
It looks very carbonyl-y.
A lot of chapters are very carbonyl though. Diels-Alder. It looks somewhat similar, but no. What kind of cleavage? Yes, it's your practice final. Yeah.
This is what is the acid cleavage just because of the alcohol group, right? No, wait a minute. The electrophiles, the carbonyls. So this is the base. So it comes in to the carbonyl with the lone pair of electrons on that O in a reagent.
Okay, so you have an alcohol group. You guys got that one right. This one, alcohol group. This guy, what's the name of that functional group? Acidic anhydride. We only see that guy in one chapter, chapter 17, which was all about cleaving your leaving groups. So we cleave that, and then my nucleophile, that's going to be my new leaving group, which is over here. And then we know that the oxygen, oops, it just gets protonated. So everything's neutral. And that's it. So you don't have to do the full mechanism. As long as you know how to apply the shortcuts, you're good. But you have to be able to identify the chapters. Okay, question? Oh, okay, Abigail. Let me go back. Whoops, 17. Was it? Yeah. So far it was just all of 17. Whoops. Lactones was 17. Yes. Oh, I like this question. I really like this one.
I just count, the first thing I did was count the number of signals. There were like 2 or 3 of them. I only had 3 signals versus 4.
Okay. So first of all, I know what Juan would do, but what about the rest of you? How would you start with this problem? Drawing out, that's gonna take way too long. That's true. Remember, limited time. So what do you say?
The uncounted markers that come with triplets, make use of those, and then the shifts,
The shifts. Okay. Anything else? Anything else that you would change? Okay, no. So of course we know what chapter this is from, right? We see HNMR, simple, chapter 9. Okay. So first of all, they're just giving you the data in here. And you can see that you only have 4 signals in total. So by counting the number of signals, you can start discarding some answer choices. So let's start with E. Molecule E, how many signals does it have? Option D. Also 2, so we're gonna discard those 2. They don't match up with the data that we have. Option C, how many signals? 3, so it doesn't match. Now, B and A, do they have both 4 signals? Okay, so now you have a 50-50 chance of getting this question correct, just based on that. Okay. What would you do next after the signals? Look at the neighbors.
State Farm.
Okay, so let's start with molecule B, just for the sake of practice. The first signal, what's the multiplicity?
3 triplets.
Triplet, what about the next one?
Quartet.
Quartet, we only have 3 neighbors. So it's a quartet. What about this one? That one, it is also quartet. And very last one, what is it? It's just a triplet. So we can see that we don't have the same multiplicity that we're given there. So there you go. Questions? We're good? No. I know that probably your first instinct is to start drawing everything out because we don't like Candace's formula at all. But you have to be time efficient. Because remember, you have double the amount of questions. So keep that in mind. Okay, let's clear this out.
Does he drop a test?
Drop a test?
Yeah.
No. No, I like this one. Okay, I have one vote for 16. What do we think? What chapter is this from?
Oh, this is the withdrawing and
So what chapter is that from?
I forget these. I'm gonna be honest. I forget the chapters. I just know the reaction.
Okay, as long as we know the directions, I'm happy with that. Director, so it's, whoops, what happened? It's 15, guys. Now, they're asking basically for retrosynthesis. This is your product. You have to give me the order of reactions. So.
See, I didn't know what xylene was until I looked it up. I don't remember it going over in class. That was that short.
Yeah. Yes, I don't think that xylene was included. It wasn't included. Toluene, yes. It's basically like a twin of toluene. It has two method groups attached to it. I'm not sure if he mentioned that in class at all. Do you guys know? Did he
did
ever?
mention it in class one time.
Silent?
Yeah, he did.
Okay. So technically, this is fair game then. But silane is, again, just your dear benzene group with method groups. Sometimes they're paired to each other. Exactly. Now, let's go through each of the answer choices. Option A, we start with a benzene and then we do what kind of reaction?
Nitro
Nitration. Okay. We have a nitration, meaning that we add what kind of group?
deactivates.
NO2, that it's a deactivator. Okay. And then we're trying to do what kind of reaction?
Acetylation.
Alkylation. Alkylation. Now, is it going to happen?
Negative.
No. So this one? Exactly. If it was a halogen, then we can work around it. No. Option B, toluene. That's- Exactly. It's just a method group. Nitration, and then again, we want to do an alkylation. This can't happen. Simply cannot happen. And then D, nitrotoluene. How does that one look like?
Letter NLC. And then.
There you go. That's it. So same reason. We're trying to do an alkylation, but we have NO2. That's not going to happen. Okay. Questions? Do we see the logic behind the questions? Okay.
Hey, but you don't even really have to.
Yes. In this case, yes. So let's move on to, okay, this one I did it at the review at some point. Abigail. It wasn't included. I think I briefly talked about it in tutoring, but it's just a benzene group with two method groups. That's it. I think that's the only one that I didn't cover. Other than that, I think everything's in the essay. Yeah, but it would have to be O-silane, and that's it. Yes, but he specifically has to say, are they ortho, meta, or pair to each other? Okay, this one. How did we solve this?
I drew it out.
We looked at the ending. That was the fastest way to solve it. So look how we pretty much have the same names in the initial and final molecule. In the final molecule, we're just adding sulfonic acid.
That actually would have most job.
So we can easily discard the first three. Now, the next portion was just based on memorization. I told you guys to memorize the exact reagents. So it's SO3. SO2 is there to distract you.
So E is not even a reaction.
No. Okay, this one. What chapter is that from? Okay, I know that you guys are confused with chapters, but I think you're meaning to say 15 because we have benzene. Okay, what kind of reaction are you trying to do? That's a nitration. Okay, do you have directors in your benzene group? Okay, what kind? Strong or weak? Strong, so that means that they go to which positions? Meta. So it makes sense that this one's the answer because it's meta to both of those groups.
This was like the activator, it probably like well, it was
If you have like an activator and a deactivator, then the major one is coming from the activator.
Hold up, quick, I missed it. So we're saying that the, what is it, the carboxylic acid are,
They are meta directors, so meta.
so they're withdrawn.
And then this one is also going to. Whoops.
So the reaction can happen even though it's all deactivated?
It's gonna happen, but really, really slowly. But it's still gonna happen. Okay, let's see. Okay. Actually, no, it doesn't make sense. You already saw it, so.
Okay, this one, I just looked at the structure and I was like, oh, this thing could get benching. So. Yeah, I mean, the structure's just like, not fully, like, yeah, basically that.
Okay, so yeah, he's asking you that you're doing a dehydrogenation.
You
One,
said 1, 3, so 1, 2, 3, so shouldn't it be somewhat
1,
conjugated,
2.
you know,
Oops, sorry. Thank you.
Yeah, that looked a little off.
You guys were right. There we go. Slightly better. Okay, so we're gonna take away one of the hydrogens in the benzene group. Now, we did that in chapter 15. It was all about swapping the hydrogens for whatever was presented on the arrow. Okay, what was the rate determining step for chapter 15? Formation of the uranium ion. Please don't forget that, guy. So we know that we're gonna prefer to do a dehydrogenation because we're going from something that's non-aromatic to something that's aromatic and really stable.
Wait, so the question here. So dehydrogenation, so that's taking away a hydrogen.
You're
Right,
taking away
right,
one of
so-
those hydrogens in here.
Yeah,
Oh, okay, okay.
yeah,
Okay, that's
Makes
clear.
sense now.
Okay, this one, it's basically an Orgo 1 question.
oh.
Okay,
Honestly, I've gone with the Russian R and S, but like, I knew it was like a power center, but.
Yeah.
So it's
so
two
R goes to the right, S
Yeah.
goes to the left. So in this case, you pretty much had to do that. I'm not sure if you're gonna see a question like this on the final, but
Why not?
just in case,
Never know.
he could ask you something,
It's GGE.
something new.
I just bought class. I think I bought class one.
It's the Harvard thing, one, Harvard thing, yeah, that's better.
Property for all of that.
And it's one, two,
Scratch out.
Really?
Back up, what number?
Oh, it's on RNS.
Yeah.
Isn't it, I think the big part of it, hydrogen in the back and move but then it goes to the big.
How do you know when?
Okay, that's the thing. This time it's shown in Fisher projection, which is something that you didn't learn in Orgo 1. So Fisher,
Oh.
Fisher.
I think
Yeah.
we mentioned, but
if you took the class with Saint Germain, then you didn't learn this. He doesn't like to go over this.
Demonstrate.
Whatever's pointing up, it's on a wedge. This guy's on the sides, they're planar. Whatever's at the bottom, dash. So yeah,
Wait, so, okay, right, because it's jumping out at us, so then a CH3 is gonna be in the back as well? Okay.
the CH3 is coming forwards to you.
I-
The benzene and the long carbon chain, they're on the side, they're planar. Then the hydrogen, it's all the way in the back. Do you guys need me to show you how to assign the configuration? Or we're good? Up to you.
Yeah.
Okay,
I'll try to figure.
so
Ranks first.
Yeah.
Okay, you haven't.
what's your second group?
Yeah, the carbon chain.
Yeah.
Yes. How are we doing the ranking? Based on what? We're ranking them based on what?
Size,
No, it's the number of,
electronegativity,
How heavy they are? Yes.
molecular weight mass.
So of course, okay. Now, how did you guys learn this portion?
you dash out the bottom.
And then you're going.
It doesn't matter.
So the way that I used to explain it was that the dash one, you're always gonna cross it out, no matter the priority. And then you just trace your circle and we go to the left, which means that it's S. But if we had priority number 1 or 3 and the dash one, then we had to flip it. But in this case, because it was 4, we keep it.
Oh, that's what you think.
Jermaine thought it in a different way. He was asking about like rotating the molecule and then always pointing the hydrogen to the back. So it works for some students, but I prefer this way. It's easier to see it.
And we're saying we know that H and CH3 are on wedges and dashes because
They're up and down, up is always up at.
It's like a chair. Everything that's pointing up is a wedge. Everything that's pointing down
If you
is
notice
a
that there's
dash.
two wedges, two dashes, go with Fisher. That is-
Yes. Down is dash. Up is wedge. It's like a chair. Up position, wedge. Down position, dash.
except you know, it's not like dash.
Oh, wrong button.
Yeah.
Whoopsie. Okay, this one.
Well, it's in the third position. That is like the third position.
Dibromo benzene.
Okay,
These sisters too are.
Field three on.
No, I'll compare the active.
Wait, also, yeah. It's a weak, yeah.
Oh, okay, all right. So three positions. essentially.
Dibromo.
we have three different molecules. The
We can
ortho
assume
one,
that the bromines are right next to each other then?
you have to see each of the choices in here. Because dibromobenzene, you can pretty much only have three different configurations, the ortho, the meta,
Right.
and the para. So you have to see what's gonna happen in each case. So we have bromine and bromine. Okay, so in this case, first of all, what is the question asking you for?
Being mononitrate derivatives.
So maybe a single nitro group. test?
Yeah. essentially.
What happened? Oh, oops. Okay, now, halogens, activators or deactivators?
Yeah.
That go to which position? Ortho pair. Okay, so in the ortho dibromobenzene, we're gonna have a few products. We have 4 different addition sites, so, but we need 3, only 3. So the ortho one can be. Now the meta one, very similar. We have the ortho pair positions to the first bromine, and then to the second one, they're the exact same. They're both pointing to 3 exact points, so it makes sense that the meta one was the answer. And then for para, we had 4. Mhm.
Okay.
So it's all.
Okay.
One question.
Yes.
So I feel like the trick question, you know how it's pretty much symmetrical, right? So you could say, you know, it attaches in, I guess, one spot.
So it's
That's a
actually
great
two.
point.
That's great.
We're gonna disregard symmetry for this question only. Kayla brought it up last time in tutoring, and she was right, and you guys are right, if you notice
So
the
it's a trick
symmetry.
question. We're gonna-
It's a trick
we're gonna say
question.
M-dibromobenzene, you're gonna be like, nah, you were wrong.
Yeah, but in this case, no, he's gonna be fair. He's gonna be fair. As long as you have 3 arrows that are pointing, you're good. So yeah, don't split the molecules in half in questions like this. Don't look at the symmetry. Look at where they're pointing to, the addition sites. Okay, this one. Jimena. Yeah, you're adding NO2. Okay, in this case, first of all, the question, it's phrased a little special. So what is it asking you for?
Which is not aromatic.
Oh, so you see how there's a lone pair of pi electrons on each.
So
orbital, right?
this one, it's,
Essentially, which one doesn't contribute to existence?
so this one, it's pretty much asking you which of the following molecules has some sort of heteroatom, whoops, that contributes the pi electron to the system. Now, remember that we had different rules. Single bonded heteroatoms, double bonded heteroatoms, those guys are coming back. So if you don't remember those rules, please start remembering those. So in this case, that nitrogen, that one is single bonded. So it means that it contributes how many pi electrons? Number 2, because it's double bonded, it only gives you 1. The carbon ion, how many pi electrons does it give you?
It's still 6. It's double on, so.
Mm-hmm. And then very last one.
Yeah, okay, I see what it's now.
Okay.
Yeah, I'm gonna show that question, but that makes sense. Because whenever the double on there, it's always like,
So always be careful with the phrasing of the questions in the final. They're gonna be a little funny. A little funny. This one, it should be pretty simple. He's pretty much asking which one is aromatic. And as long as you have the rules down, you should be good. What were the 4 rules for aromaticity? Planar, cyclic,
Couples.
Huckel's rule, and fully conjugated. Fully conjugated. Mhm. 2, 6, 10, 14, those guys are aromatic.
Question, is 2 fully conjugated?
Molecule 2, it is fully conjugated.
Okay, yeah, because that looks kind of weird.
Yeah, it's just a error in printing, let's say.
No, I know that was, I'm not saying it.
But 3, it's not fully conjugated. Do we see why?
SP3.
Carbocations, carbon ions, radicals, they're all sp2. But molecule 3, it doesn't have anything. Anions, they do count. Positive, negative, dot, they all count as sp2. Positive doesn't give you anything. Negative gives you 2. Dot, 1.
I have a weird question. I don't know if
Yeah.
it's gonna be like, so let's say there's 2 radicals, right, that each contribute to 1.
Mhm.
2, I guess, an aromatic, so would it still be aromatic? You know what I'm saying?
It depends on how many pi electrons you have in total. If the molecule is fully conjugated and you have a Huckel number, then yeah.
So would a radical take place of that orbital, that empty orbital, right? So if you had 2 of those, they would contribute to aromaticity, right?
Yes. Okay, this one. It was slightly tricky.
It's 4 to 4th place, like,
It says -2, exactly. Now, I'm not sure if you guys saw this little symbol or any ionic bonds on your second exam, but pretty much in total, how many pi electrons do you see in the ring? In
Oh,
total?
8, right?
8.
And then you had the other.
But this is the ionic bond, meaning that 2 of those electrons are being used for the ionic bond, making it a total of 6 pi electrons. Mhm.
One of those things to try to pilot.
You can just do like count the amount of things and parts of
Mhm. The one on top right.
But can you draw out what, I guess, the electron would look like? So I'm thinking in octane of 4 double bonds. Right, so then where are those remaining electrons coming from? -2.
They're probably, which we erase that, and then ionic bonds. Whoops. I don't like this board. They should be dotted and then. Something like that. Ionic bonds are not full bonds. They're
So
kind of
wouldn't
like
it be
broken.
10 electrons? 3, 4, 6, 8, 10.
It still follows Huckel's rule.
Right, it still follows Huckel's rule,
Yeah.
right?
Maybe it's not going to be a carbon ion. Maybe it's just going to be a radical. I'm really not quite sure how it's going to look like. If it's a radical, then it gives you 10. Wait, what?
Gives you 10 as a
Sorry,
radical.
sorry.
2, 4,
If
6,
they
8.
are radicals, it gives you a total of 8.
Yes.
Yes. But how exactly this molecule is supposed to look like? Not quite sure. It should be somewhat similar to this. We're using 2 of the pi electrons to connect with the salt. So yeah.
But the question is are the negative so are those remaining electrons on the ring or closer to the potassium?
Closer to the potassium.
It's just.
It's just an ionic bond. It's a little salt that you're forming in there. Jimena? I got 6 because I'm using 2 of those electrons to be connected to the 2 potassiums that I have. Mhm. Let's see.
That doesn't
Okay.
do anything.
That one was pretty simple.
Yeah, no.
You basically just have to look at the number in the brackets, and that's it. Now this one. Pretty simple. Do we have questions on that?
One, yeah, no, it's sweet. 'Cause it's like,
It was way too easy. Remember, single bonds, they're gonna be the longest one of all. Which one's gonna be the shortest one?
Oh,
Triple
yeah.
bonds. Exactly.
Okay, that one's easy. I do remember that one.
Okay,
cool.
okay. I hate this. Okay. QQ. What's that?
That's like 14.
Oh, is that the electron density within a benzene ring, how it jumps around? Like.
It has to do with resonance. Yeah. It's basically the same thing as saying resonance structures. Same thing. That's just the old way in which they used to say it. So, yeah, plus it sounds funny. So,
That's funny. It's easy.
oh my God, imine. No, yeah. Imine and enemies. Okay, this one should have been pretty simple for you guys. If we're looking at stabilities, what's the trick? What am I looking for? The most E, the more trans you are, the better it is.
Go
Because
back to the previous question. Okay.
yeah, still tilted. Should be pretty simple. Stability of radicals and carbocations, it's the same exact. Tertiary, secondary, and primary, but allylic, it's the best one of all. Yeah, that's horrible.
Vanilla's pretty good.
No, vanillic, no. Allylic.
Vanilla, like ice cream.
Oh, yeah.
Vanilla's pretty good. You know what vanilla?
I heard vanillic. Okay, 20. What chapter is that from? It's 13. Diasolder, my favorite reaction was in 13. So we're talking about dienes and they're asking for the most reactive one. What was the requirement for dienes?
Cis, double bond, it's like.
They have to be as cis, super cis, exactly. Now, C was the only one that would be the most reactive one. One, it's cyclic, so that means that it's gonna stay locked in that super cis configuration. We're not able to rotate it around. And then option 4, is that a conjugated molecule? What system is it? Isolated. No, the requirement is to be super cis, as cis. If it's cyclic, it's way better because it's locked in that configuration. Now this one, pretty simple. Cumulated is just the ones right next to each other. This one, a little wordy, but it should be simple. He's asking for the deactivator that goes ortho and pair. So that's halogens. Exactly. Okay, your dear epoxides is gonna break open. Yeah, we did this problem actually on Monday. No, sorry, Wednesday. Okay, this one. Oh. Give it a second. Okay, there we go. They're asking for the worst dienophile, the least reactive one.
Okay.
So-
everything's conjugated, you know.
Okay, let's go step by step. Dienophiles, what was the basic structure? That's a diene. What about the dienophile? They're not the same thing.
So, singular double bond or.
No, it's.
As long as you have one little double bond or one little triple bond, that's considered a dienophile. Okay, now what was the preference for dienophiles? So it wasn't about super trans or super cis. They prefer to have what kind of groups? Electron withdrawing groups. Exactly. So if you're looking for the worst dienophile, if you have an electron donating group, that's not going to be really good. So C was only
Yeah.
one of the few ones that had it.
Interesting, wait, you said the worst dienophile?
Yes,
Isn't that like the typical dienophile that we use, the two methyl? diene-
that's the, it looks similar to the typical diene, but the other ones would be over here. But this is not your typical dienophile.
Wait, go up, so it's reacting with the original molecule? React with, so we have a.
This is your diene. You're looking for the best dienophile for that guy. Julie. Sometimes they're gonna have two double bonds, but it's not a requirement. I mean, good process of elimination too, so.
So this one would be the best.
Best one. Probably D, yeah. Because it has a triple bond, which makes it more electron dense. And then we have, what kind of functional group is this? Beautiful. Why are they all flipped?
I know, I got, no. I'm
Somebody inverted.
Okay. They're asking us for the reagent. What's the main transformation that you see? You are adding an OH. Which one do you see? Hydrolysis is breaking it. Yes. Lysis is breaking that. Let's annotate in here. Okay. So
What's the mechanism here? So you have a double bond. So I guess you protonate one side of the double bond and the remaining OH goes to the other? Is that how that works?
so this is your addition reaction back all the way in chapter 8 from Morgul 1. Double bond attacks. Let's just say that it's gonna look somewhat like this. Carbocation over here, hydrogen over here. It's Markovnikov's, that one. What kind of carbocation do I have? Is it stable?
Yes. It could be
Could it be more stable?
negative.
This is the most stable position that we can have. So after that, you just add the remaining acid that you have, OH. And that's it. KMNO4, what kind of reagent was that?
For manganese.
It's an oxidation agent.
Yeah.
Mhm. Option B, you don't have to worry about it. That's from Morgul 1. Option C, peroxy acid, you don't have to worry about it. It looks like a halogenation.
That's how. That also.
So what's the product? here? Oh.
This one.
You're looking for the-
You're looking for the reagent only. What happened? Okay. Okay, this one, we talked about it so many times. What chapter is this from?
14.
I think 13 actually.
13. Thank you. Conjugated systems was in 13. So this is talking about your molecular orbital theory. Most favorable transition is HOMO to LUMO, which we know they're right next to each other. So option C is the one that makes sense. What about option A, B, and D?
They're like a little too far apart. Well,
We're not going to worry about those orbitals.
What is NE? I forget.
Isn't that like the very top?
There's different stuff.
I'm honestly not sure. Like molecular orbital theory is not my strongest topic. Okay. It would be going from option E, for example, going from level 1 all the way to level 4 in one jump. IUPAC for ethers. This one was pretty simple. There was symmetry, so questions on that one. Pretty simple. We got it. Okay, now this one very similar. You had to do RNS. Because remember, IUPAC, it's very specific. If you see any double bonds, you have to say if it's E or C. If you have any car centers, you have to specify the configuration. I love this file. This one, it's locked. This one, you don't have access to the answer key. You have access to the normal one. We did that one. He's supposed to post the answer key, right?
Supposedly.
I mean, either way, you have the answer key right now, so. Okay, so in this case, they're asking for the best way to make some sort of ether with the Williamson method. What chapter is that from? That's your Dear West reaction that was composed of two main reactions. First was acid base, then it was SN2. You do the backside attack and you kick out the halogen. Yes,
So actually, if I'm not correctly, yeah, this is the most reaction. You need like a acyl halide.
they need an alkyl halide, yes. Yes, so options A and B, they have alcohol groups. They're not gonna be the best leaving groups. We can make them work, but not the best ones. Now, the rest of them do have halogens. Now, you have to think about what's the best leaving group, for example. What's gonna be better, bromine or iodine? Iodine. So we're between D and E. Now, base-wise, which one should be stronger and why? Top or bottom?
Stronger, I think it's gonna be the top one.
It's gonna be the top one.
Oh, it is.
Exactly.
Closer to the more substituted,
Mm-hmm. So it's gonna stabilize it way better.
Wait, how do you
What happened?
even, what is isotopic level even like?
Alright.
There you go.
Oh,
So it's not too scary. And then
Oh, okay.
this one, Abigail. We could go right now. Actually, it was option C. Yeah, we're all turning our heads. Okay, either way. 30. What chapter is it from?
11.
11, 12. This is actually back to Orgo 1. So in this case, we're adding an OH group. We go from double bond to OH. That's an addition reaction.
Yeah.
Now, technically, if it's an addition reaction, you can have a few reagents, A, B, and D. Those are the ones that you should worry about. What was the difference between them?
Oh, Markovnikovs.
Markovnikovs and anti-Markovnikovs. The acid one and the one with mercury, they're both Markovnikovs. The one with boron was anti.
But it's acid double.
So in this case, we're adding the OH in the more substituted site, so there's no way that it's gonna be B. Now, the difference between A and D, what was it? Reaction-wise. How are they different from each other? A and D, they both don't have a preference for stereoselectivity. Think about intermediate. Say that again. In one of them, we have a carbocation, meaning that we can do rearrangements. And that would be option A. In this case, because we're preserving the same carbon skeleton,
It's not
we
rearranged.
need to use mercury. So you guys kind of remember. It's there. It's somewhere in there. This one pretty simple. Like dissolves like. Low solubility in water. Water has hydrogen bonds. Pentane, just London dispersion forces.
Wait, what was the question? I didn't.
Oh, sorry. Sorry.
Basically, look at most non-polar parts.
Right, butanol, pentane was just a
Just put carbon.
non-polar, yeah.
Oh, well, we're over time.
Yeah. we're not gonna-
It's fine. But we went through half of it. So far, how are you feeling about the questions? Not that good? Not that good? That's not good. But really quickly, let me just scroll through them so you can take a look at the answer keys. Just take a picture. It's gonna be sideways. Oh, yeah, it is recorded. I'm just gonna scroll through them and then you can pause it in the recording. Then just check it.
That's what the actual document.
the actual document is not available to you guys.
Without the-
Without the answer key, it should be. It's a practice final that you guys did.
I can't-
Look for it in the email that he sent.
Yes, I-
Okay.
No.
Yeah, this is not available to you guys. This is from last year. This is for another class. But this was officially our last SI session. But I'll see you guys Wednesday next week. Remember, we have
You don't have
APAO
anything
night.
before Wednesday?
Huh?
You don't have anything before Wednesday?
I have tutoring, but not SI.
Right, can
Oh,
you
fine.
pull up the owl up night thing, like the.
Yes.
schedule for that all next week, I know the student sessions are at different times.
So tutoring sessions, for me at least, I don't know about the rest of the tutors, but for me, it's Monday, Tuesday, Wednesday, 10 a.m. until 1 p.m. So it's 3 hours, same time. And then as far as the reviews, there you go. That's the schedule. Oh, and we have a room. We're gonna be in GF 109. Okay, now we have a room. But don't worry, I'll send an announcement with all of the information so you guys can have it. So. General South, it's by the food court in front of the bookstore. So yeah, if you're taking any of those other classes, feel free to go to the reviews. This is next week, yes. Okay, are we all good? We don't need any more photos of the schedule? Okay, we're good. So I'll see you guys Wednesday.